So way back in lecture Fields and Waves Part 4, we introduced electric field, we introduced electric charge, and we talked about Coulomb's law, which was a straightforward way to relate what kind of electric charges lead to what kind of electric fields. However, Coulomb's law is really not all that applicable for a number of reasons that we'll talk about later. So in this lecture, we're going to talk about something called Gauss's law, which is a much more general and useful way to relate electric charges to electric fields. This lecture is divided up into two pieces. In part one, I will introduce Gauss's law. In part two, we'll talk about how it's applied in a few different situations. All right, so let's start out with what is Gauss's law? All right, so I'm going to go back to the analogy of water flow to describe electric fields and sources. So imagine this scenario. We've got a spout over here, an electric spout, and I sort of talked about earlier that we can describe electric charges as being sources or sinks, right? So positive charges are going to be like sources that are spewing out electric flux lines, and negative electric charges will be like sinks. They're going to suck in electric flux lines at a given rate. And so let's just sort of describe this pictorially. And the long story short is that Gauss's law is just going to be a mathematical embodiment of that fact. All right, so here we've got a source, an electric source, which I'm going to describe as if it were a pipe, sort of bringing water to the surface and spewing it out at a certain rate, some number of gallons per minute. And over on this side, this is going to be a drain or a sink that's sucking in water at a certain rate. And so this is a source on the left. All right. Now imagine that this is all in a big pool, right? So these pipes are sort of in the bottom of a pool. And so you've got the water level on this pool as well. If I drew this scenario for you and I asked you to map at this location here, where I just drew a green dot, where do you think the water is flowing? Right? You could probably give me an answer because you've got water spewing out from this pipe over to the left and it's being sucked in by this drain to the right. And so it stands to reason that the flow of water will also be toward the right. All right, so there's definitely a connection between where the sources and sinks are and where the electric flux lines are. Remembering that the flow of water in this diagram is kind of analogous to electric flux. All right, we call that D. D was electric flux density, which is closely related to electric field in that all you got to do is multiply the electric field by the permittivity, and that gives you this flux density D, whereas E is the electric field, and that's connected to the forces that are on charged particles. All right, so that's one perspective, but let's also look at this with sort of an overhead view, right, of the same situation. Let's say, for example, I've got a positive source right here. So this positive source is spewing out electric flux lines at a certain rate. And I've got a negative sink right here that's sucking them in. And let's say I drew a little circle around it. All right, again, this is an overhead view looking downwards at a pool. And at the bottom of the pool, you've got pipes, which either source or suck in water. And you've got a water level, which is whatever, a couple, let's say a few feet over the floor of the pool. And I asked you the question, if I took this circle that I drew around these two sources, and I asked you the question, what's the total flow of water out of or into this circle? What would your answer be? Right? And so the way that would work is in each of these little pieces of the circle, I'd ask the question, is water moving out or is it moving in? Right? Outward flow or inward flow? So you could, in principle, put down a little probe in each one of these locations and measure where the water is flowing. And if you added up all those little contributions of the entire surrounding circle, you'd be able to calculate, okay, there's a total of 5 gallons per minute going out, or 5 gallons per minute going in. And so in this case, though, consider the fact that we've got both a positive source and a negative sink at, let's say, equal rates. What that should tell you is that there ought not to be a net flow through this circle, right? Because for every gallon of water per second that is sourced by the positive, there is another gallon per second that's sucked in. And so if we draw this scenario and I say, well, what's the outward flow or inward flow? It should be equal to a similar situation where I'm just going to redistribute the charges. Let's say I've got a big charge over here and I've got a negative charge over here. And now I draw a surface that looks like this. Right, still kind of a wacky surface, but it encloses both that positive and a negative charge. I ask you the same question, is total flow of water outward to inward? And your answer should be the same. There is no net flux. And so what Gauss's law tells us is that if I have an enclosed surface, I can say something about what is the net charge inside that surface by relating it to the total flux of electric flux lines through the edges of the surface. But it doesn't matter where those charges are distributed, right? I can take this positive charge and I can move it over here, and my answer will still be the same. There's no net flux through this surface. The answer to the question, where is that flux distributed, might change. So I might get lots of positive flux over here, and I'm going to get some negative flux coming in there that's drawing in electric flux lines. And as I move the charges around, where I've got positives and negatives might change, but the total sum of everything is a constant and is only related to the total sources that are inside. All right, so Gauss's law is really just an electrical equivalent of that. Right, and Gauss's law is stated as follows, that if we take the integral over some closed surface, a closed surface is a sphere, a cube, anything that's got a volume inside of it. And we're going to take the electric flux density, and to calculate the total flux that's going outside or inside this closed surface, we're going to dot it with a differential surface. Right, so this is a surface integral, and if we do that, that's going to equal to the total charge that is within this enclosed volume. And so for that, we're going to take an integral over the volume that is within the surface, and so we're going to take the integral of the volume density integrated over the volume inside. All right, so this is the outward flux, or the outward flow of electric flux. Right, and this right term here is the total charge in the enclosed volume. All right, the units do work out, by the way, because D, we called D electric flux density. And it should hopefully make a little more sense now why we called it that. Electric flux density in units of coulombs per meter squared. So it's a density, we multiply it by a little piece of an area and we get electric flux, right? So one small piece of D dot ds gives us a contribution in one little area of total electric flux. And we're summing up all those contributions with this integral right here. And so we're multiplying this by a differential surface, which is a meter squared. And so the units of this entire thing has units of coulombs. The right side is also a total charge. This is rho v is a charge density per volume. So it's a coulombs per meter cubed times a meter cubed. And so this also has units of coulombs. Right, so it should make sense now why D is electric flux density, because it's a density of electric flux, and if we integrate it and multiply it by area, then we get total flux or total flow of these electric flux lines. All right, another sort of a qualitative way to state what this means is that electric flux lines, I'm going to underline flux to remind you this is electric flux, not electric field. electric flux lines start at positive charges and end at negative charges. All right. Electric flux lines will not start on anything other than a positive charges, nor will they end at anything other than a negative charges. And this makes sense because we've been ascribing positive charges as sources of electric flux lines and negative charges as sinks that are sucking them in. So this is really all that Gauss's law is in this form. It's worth taking a minute to contrast this to Coulomb's law, right? We introduced Coulomb's law, and we had this great way to take a set of charges and relate it to electric fields. So why do we need another unit to do that? What's the point? So couldn't we have just stuck with Coulomb's law? So both are certainly useful and in certain means, but Gauss's law is more general. We're going to talk later about why it's more general, but you can derive Coulomb's law from Gauss's law. So this is the more general version of it, but you can't go backwards. You can't figure out what Gauss's law is if you just had Coulomb's law. So Gauss's law is more general, so that's number one. Technically, Coulomb's law is only correct for statics. All right, so let me just try to summarize this. All right, so number one, Gauss's law can be used to derive Coulomb's law, but not vice versa. All right, so that's number one. Number two, Coulomb's law only works for statics. By statics, I mean situations where nothing is changing with time. If anything is moving, if anything is growing or shrinking as a function of time, then you can't use Coulomb's law, right? Where nothing is changing with time. All right. Gauss's law also has a much more useful differential form we're going to cover in the next lecture. Okay, Gauss's law has a differential form. All right. And so those are the big reasons why we're introducing Gauss's law instead of just sticking with Coulomb's law. All right, now, well, we're going to talk in the next video about also why this particular form of Gauss's law is really kind of useless on its own. It's worth introducing it as a concept because it, again, establishes what exactly an electric source is or what exactly an electric charge is and how it relates to this electric flux density. But this form itself, not going to be so useful. In the next lecture, we're going to talk about why that's the case. But before we do that, in part 2 of this lecture, we will see a couple scenarios where Gauss's law in this particular form, called the integral form, is helpful.